Hello, Mark McAvoy, interview part 2 for Princeton Review. Now presenting on the calculus review section, specifically integrals. Beginning with the integral symbol. This long, elongated curly S kind of looks like is the universal notation for the integral. We accompany this with some function, fx, and dx. dx indicates what we are taking the derivative with respect to. So here it's not with respect to x, it's with respect to what x is being evaluated on, and that is x. Also note, it is important to always include dx. It's common for beginning calculus students to forget this notation, but you want to always remember it because there are other kind of integrals. What we're learning here is called the Riemann integral. There's also the Riemann-Stieltjes integral that uses d alpha x, and also the Lebesgue integral. The importance of this is what is being measured on, but it's kind of, we don't need to go into that right now. So beginning with what the idea of the integral is. So for a function, for a function fx, we call the antiderivative of fx. We write it with big notation fx. What does this mean? Here's an example. X squared is a common example. We take the derivative of it, and we get 2x, which you should know from prior calculus. Bring the 2 down, minus 1, left with just 2x. And then going the other way, that x squared is the antiderivative of, this is kind of what we're thinking of as the reverse process for the integral. So we can write in parentheses the integral of, but what it actually is just the antiderivative of. And so here, going from x squared to 2x is clearly the differentiation part, and then going from 2x to x squared is the antiderivative part. That forms the fundamentals of finding integrals of polynomial form. And how, you may ask, do we find the antiderivative if we say are given with just 2x, that we don't want to always, if we aren't starting here and going around, if we are just given 2x, how can we move to this? And the answer is using the power rule. So for a function fx of the form x to the n, the integral of x to the n with respect to x, no, we're not writing dn or df or anything, we're writing dx, that this is equal to x to the n plus 1 over n plus 1 and plus c. Coming back to the c in a moment, that what we have done is we've gone to the bottom part, that we have found the antiderivative of x to the n, and so if we were to go to the top part of the diagram, if you remember that, or if you can record, if you can go back in time. when we all love to do that, is you can take the derivative of x to the n plus 1. This is going to bring the n plus 1 down, cancel with the n plus 1 on the bottom, and then minus 1, get x to the n, and so that justifies, gives reason to believe that the power rule that we're using is right and makes sense. Further, if we were to include the c, that if we were to take the derivative of the entire side, that is I'll just give an example of 1/2 x to the squared, this entire thing plus some constant, let's say 1, that this is going to give, just bring the 2 down, cancel, and so just x, plus it's going to be 0 because, as you know, the derivative of any constant is 0. So if we change this to -1, still 0, to 100, anything, it's always going to be 0. So that's why we include the constant, and also why the antiderivative has an infinite number of solutions. An example is find the integral of x cubed. I'll give the class 30 seconds to solve it. 1, 2, 3. Time's passed. This is going to be using the power rule. X to the 3 plus 1 over 3 plus 1 plus some constant. That's just x to the 4th over 4 plus some constant. Also note what we're doing are called indefinite integrals. If we had a definite integral, that is that we're evaluating from, say, a to b over x, that we could then solve for c, but we're going to get to that in more detail later. Not in this presentation, but like say in a different class. Next is example. Find the antiderivative of x to the -3. What do you think we do? We use the power rule. It's the only thing we've learned so far. We do -3 plus 1 over -3 plus 1 plus some constant. And that's just x to the -2 over -2. Plus some constant. So in general, we can also conclude if fx is some function and fx and gx are some function, and k is some constant, then the integral of k to the fx is going to be that we can bring the k in front. So writing that now. Yeah. Next is the integral of two functions, the sum of two functions. It's equal to, I think I kind of run out of space, so I'm going to write it over here. It's equal to the integral, the sum of the integrals of these functions. I almost forgot the dx. And lastly, yeah, good. The integral of a constant is going to be the constant times x plus some other constant. Not the same constant, a different constant. We can actually conclude this from the power rule if we combine this here with the power rule if we take x to be raised to the 0. So that would be integral of k of x to the 0 dx is going to be, bring the k in front. And then that's k x to the 0 plus 1, that's just 1 over 1 plus some constant, and that's exactly written, what is written up there. Good. And next, okay. Next, going to do a trigonometric integral. Remembering what the trig functions are. Say the derivative of sine x is negative cosine x. You have on your paper a list of some common trig integrals. Just going to let you read through that on your own and go on to the first example, which is evaluate the integral of sine 5x. So think, what is the reverse derivative, the antiderivative of sine x? That's going to be cosine x, but also remember when you take the derivative of cosine x, it gives a negative sine x. So we're going to have to further include the negative here. So that's going to be equal to the antiderivative of sine x. Is going to be negative cosine 5x. But also note, when you take the derivative of trigonometric identity, that includes some constant inside the evaluation that is brought in front by the chain rule. So here we have to do the opposite of that. We'll have to divide by what is inside this, which is the 5, so we divide by 5. And add some constant. Okay. That's good. And I will conclude with doing an extended polynomial example, that is evaluating the integral x cubed plus x squared minus x dx by one of the rules that I just erased, is that x squared is integrable, x cubed is integrable, x squared is integrable, and so is negative x. And so the sum of these is going to be integrable, and that we can separate them into the sum of each of their respective integrals. So this is going to be equal to x cubed plus x, forgot the dx plus the integral of x squared dx plus the integral of x dx. And using the power rule, this is just going to be x to the 4th over 4 plus some constant, let's say, some constant c1 plus x to the 3 over 3 plus x squared plus some constant c2, let's call it, plus x squared over 2 plus some constant c3. But we can combine these, since these are arbitrary constants, we can combine them all into one big constant, let's call it just big C. So this is going to be left with x to the 4th over 4 plus x to the 3 over 3 plus x to the squared over 2 plus some big constant, where C is equal to C1 plus C2 plus C3. And that finishes my presentation. Thank you.